In this video, we'll cover risk and uncertainty in the context of individual assets. First thing we'll define is what's called a probability distribution. For any quantifiable outcome, called random variable, any set of possibilities and their associated probabilities, a list of all of the probabilities and outcomes is called the probability distribution. For example, the variable might be tomorrow's high temperature. You would list off the different levels we could take, maybe 50 degrees, 51 degrees, 52 degrees, the probabilities of each of those occurring, and that would be the distribution of tomorrow's high temperatures. You might have a stock return that might return 3%, 4%, 5%. You take the probability of each of those, list them out, and that would be the probability distribution of stock returns. I can illustrate all the things we need for this class using a particularly simple distribution that reflects the aggregate uncertainty in the economy and the individual uncertainty of the strategies of specific firms. So what we're going to do is we're going to assume a particularly simple distribution for the point of illustration. That distribution will be Washington's policies, a quarter flip, determines general economic conditions either good, the probability of a half, or bad, with a probability of a half. Then individual companies like Roosevelt Routers, represented by a dime flip, will either make good strategic decisions or bad. If the economy is good, and Roosevelt Routers makes good decisions, probability a half, then Roosevelt Routers will have a high return of 15%. Probability that the economy is good, a half, times the probability of good decisions, a half, is a quarter of the time, we'll end up here. If the economy is good but Roosevelt makes bad decisions, if the economy is bad but Roosevelt makes good decisions, we end up with a 5% return. Half the time, half of that time is a quarter, half the time, half of that time is a quarter, so altogether a half of the time we'll end up here. If the economy is bad and Roosevelt Routers does poorly, we'll end up with a negative 5% low return for Roosevelt Routers. Suppose we have the same thing for a company called Jefferson Jingles. Just like Roosevelt Routers are affected by economic conditions, good or bad, probability of each is a half. Good decisions in a good economy lead to a 25% return a quarter of the time. Bad decisions in a good economy lead to a medium return. Bad economy but good decisions also lead to a medium return. Bad economy, bad decisions leads to a low return. These are two probability distributions. If I put them together, what I get is called the joint probability distribution, a list of all the different combinations of things that can happen in the probabilities. Half the time, the economy does well and half poorly. Given that half the time, Roosevelt Routers does well or poorly. Given Roosevelt Routers does well half of those times, in total a half, or an eighth, what we get is both companies, Roosevelt Routers and Jefferson Jingles, doing well. But if the economy does well, Roosevelt does well, and Jefferson makes bad decisions, that also happens a half, an eighth of the time, we'll get a high return on Roosevelt but an average return on Jefferson. And this just lists all those possible combinations. Each one has a probability here, very simple, just an eighth. We represent the distribution and the uncertainty of the distribution by a histogram. Half the time we get the median 5% return for Roosevelt Routers, or 7.5% return for Jefferson Jingles. A quarter of the time we get a low return, but notice that it's lower for Jefferson Jingles and Roosevelt Routers. A quarter of the time we get the high return, but notice it's higher for Jefferson Jingles than Roosevelt Routers. Jefferson Jingles is more spread out in their distribution. It entails higher risk. The first thing we'll want to measure is what we expect to get on average, or the expected return. The way you do that is you sum. Now this is the Greek letter sigma here. It means add things up or sum them. We'll be summing across outcomes what we actually see, the return, times its probability. So every outcome, you take the chances you see it times what you see, add them up. That's called the average or expected return, sometimes called the mean, denoted by mu, of the return. Now, if you're working with historical data, like you've got 60 months of monthly returns, each one of these probabilities is 1 over n, or 1 over 60, and each of the returns in this formula is the actual return in a given month. So this formula is pretty easy to implement. If you have the list, you just multiply. And then you add them up. In this case, you can collapse these. A quarter of the time, you get 15% return. A half the time, you get 5% return. A quarter of the time, you get minus 5%. Add them up. We'll just go ahead and do this in the calculator here. Return plus, in parentheses, a quarter of the time, I get a negative 5% return. So the average return here, the expected return, is 5%. I'm going to store that so I have it for later. You can do that for Jefferson Jingles. This is all written out. An eighth of the time, you get a high return, and so does Roosevelt Routers. An eighth of the time, you get a high return, but Roosevelt Routers is medium. An eighth of the time, you get a medium return, and Roosevelt gets high. These are just all of the combinations. Add them up, you get 7.5%. Next thing we'll do is measure how dispersed that distribution is, how far away from the middle we expect to be in any typical observation. That's measured by variance, or more commonly by something called standard deviation. So the idea is we want to measure how far away we are from what we expect it to be. The way we measure that is with the deviation. It's what we actually see minus what we expected for every possible outcome. Then we want to measure how far away we are, not exactly what that deviation is. So to turn these all into positive numbers, we square them. We weight them by the chances we see it, so probability times deviation squared. And then the last thing we do is add them up. That's the summation sign. Now in a calculator, it's often easier to just add up the return squared times the probabilities. If you do a little algebra, you'll find that that gives you exactly the same number if, at the end, you subtract off what you expected squared. In fact, that's what I'll do on the calculator here in a second. Now this gives you how far away you are from average in what's called Euclidean distance. That's in return squared here. And return squared is not a very meaningful number. To turn it back into returns, what we do is we take the square root, and the end result is what's called the standard deviation. If you have historical data, you're going to divide all these things by n minus 1. So if you have 60 months, you'll divide it by 59. And the reason for that is that observationally in any finite data set, the worst and the best outcomes probably don't happen. So on average, you're underestimating the standard deviation. This corrects for that. So in our case, we'll do it for Roosevelt Routers. Now what you do is you multiply by the return squared. And then at the end, you have to subtract off the expected return squared. Now this also collapses. A quarter of the time, you're getting 15%. Half the time, you're getting 5%. A quarter of the time, you're getting minus 5%. You expect 5%. That'll give us the variance. So we'll do that on the calculator here. So a quarter of the time, you expect, in parentheses, 15%. I'm going to square it. Plus, in parentheses, a half the time, multiplied by, in parentheses, you expect 5% squared, plus, in parentheses, a quarter of the time, times, in parentheses, you get 5% negative squared. Now I'm going to subtract from that, in parentheses, 5%, the expected return squared. Okay, this gives the variance, usually denoted by sigma squared, .005. The standard deviation is the square root of that, 707. I'm going to store that so I have it for later. You can do the same thing for Jefferson Jingles. This is calculating them all out. This is doing the subtraction first. What you get when you get all done is 14.36%. Now what I've done in the calculator is I pre-calculated that and stored it in another memory register. Finally, we're going to come up with a topic called correlation. It's the tendency of two different things to move in the same direction at the same time. So a correlation for returns is going to be calculated using whether or not they return more or less than you expect at any given point in time. Now this covariance and correlation is going to be very important for us because it determines whether or not risks of investments offset each other or reinforce each other. Variables with positive covariance or correlation tend to move in the same direction at the same time. With negative correlation or covariance, they move in opposite directions in a given time. So if I were to build a portfolio of multiple investments that are all moving in the same direction at the same time, those risks don't cancel each other out. In fact, they might tend to reinforce each other. If I have some investments that are moving in one direction and others that are moving in the opposite direction at any given point in time, those two things cancel out risk. So this is going to be very important for determining the overall risk of a set of investments for a company or a set of stocks in a portfolio. So things that move together at the same time, positively correlated, like these two stock prices here, they have risks that tend to reinforce each other or at least don't cancel each other out. So if I were to build a portfolio of these two stocks represented by the yellow line, what you would find is the portfolio moves around almost as much as the positively correlated stocks. But if they're negatively correlated, risk tends to cancel out. So the yellow line portfolio here doesn't move around as much as either individual stock. Again, that'll be important when we look at sets of investment projects or sets of investments for a portfolio. So how do we measure this? Well, what we're after is the tendency for both of the stocks to be above or below average at any given point in time. So what we'll do is we'll take every one of the outcomes, probability of the outcome, chances you see it, whether or not you did better or worse than you expected in the first investment, better or worse than you expected in the second investment. We'll multiply those two together. If you do better on both investments, both of these numbers are positive, this will be a positive number. If you do worse in both investments, they're still moving in the same direction at the same time, the negative times the negative creates a positive number. If they move in opposite directions, one's positive, the other's negative, then you get a negative number here, and it tends to reduce correlation. Now again, if you do a little algebra, the easier way to do this is probability times return, subtract off the two expected returns at the end. Again, when you're done with this, you end up in terms of return squared space, which doesn't make much sense. The normalization here is a little different than variance to standard deviation. You divide through by the two standard deviations. That controls for the natural risk of each of the individual investments and allows you to focus on their tendency to reinforce or cancel each other, the correlation. Correlations then range from -1, they always move in the opposite direction by the same relative amount, to +1, where they always move in the same direction by the same relative amount. 0 in between is no particular relationship. What I want to do here is just show you how to calculate it. We'll take this distribution. All 8 outcomes are important here. because all 8 outcomes represent a different configuration of one company or another company doing better or worse. So how would we add these up? Well, the easy way on the calculator is just take the probability times each return. And then you add them up. And what I'm going to do in the calculator is I'll do each one of these individually and store them and add them up. At the end, you take off the expected return of the first stock times the expected return of the second stock, and you have the covariance. Right? So that's what we're going to do. So every one of these is an eighth of the time, an eighth of the time. At the end, the correlation we're going to divide through by the 2 standard deviations. Recall that the first standard deviation is 707. I'm just going to multiply by the second standard deviation, 0.14, and I'm going to store that number because that's the number I'm going to divide by to get the correlation. All right, now we'll just calculate this all out. Starting at the top row, an eighth of the time, we get 15%, an eighth of the time, we get 15% and 25%. An eighth of the time, it's 15% and 10%. An eighth of the time, it's 5% and 25%. An eighth of the time, it's 5% and 10%. Now, that's number 4 and number 5 are exactly the same, so I'll just store that again. And an eighth of the time, you get 5% and 15% negative. An eighth of the time, you get 5% negative times 10%. And an eighth of the time, you get 5% negative times 15% negative. We're going to add these all up. Then we're going to subtract off the expected return of the first stock, this is going to be in parentheses, times the expected return of the second stock. And you get the covariance of 0.005. The correlation is that divided by the 2 standard deviations. Remember, they were 707 and 1436. Remember, I already multiplied those 2 numbers together, so I can just divide by those 2 numbers already multiplied together and get 0.4923. This represents some tendency to move in the same direction at any given time because of better or worse economic conditions, but a considerable difference in returns across these 2 companies because of their independent strategic decisions that allow the companies to do relatively better or worse in good or bad economic times.